Somewhere beneath the border of France and Switzerland, 16 miles of tunnels sit 300 feet underground. Inside, protons accelerate to almost the speed of light and smash into each other with enough energy to briefly recreate conditions from the first moments after the Big Bang. Scientists built this machine to answer one question. A question so strange it sounds impossible. Are there dimensions of space we can't see? We're going to hunt for hidden dimensions, microscopic black holes that vanish in a trillionth of a second, and a particle that might be escaping our universe right now. If you enjoy the ride, subscribe and like. We're just getting started. Pick up a refrigerator magnet, hold it close to a metal surface, and let go. It snaps right on. That tiny magnet, weighing maybe an ounce, just beat the gravitational pull of an entire planet. The whole mass of Earth, 6 septillion tons of rock and iron and molten core, lost to a piece of painted metal you bought at a souvenir shop. That should bother you. A lot. Gravity controls planets. It holds the moon in orbit. It keeps our atmosphere from drifting off into space. On a cosmic scale, gravity is the king of all forces. It shapes galaxies, it bends light, it determines the fate of the universe itself. So why can a toy magnet embarrass it? Physicists have been sitting with this question for decades, and the answer they keep landing on is deeply unsettling. Gravity isn't weak because it's a small force. Gravity appears weak because most of it is somewhere else. It's leaking, bleeding out into directions we can't see, into dimensions that our eyes, our instruments, and our entire understanding of space simply do not register. That's the hypothesis, and it's one of the most serious ideas in modern physics. The gap between gravity and the other fundamental forces is enormous. Electromagnetism, the force that makes your magnet work, is about 10 trillion times stronger than gravity at the same scale. The strong nuclear force, the one that holds atomic nuclei together, is even more powerful. These aren't small differences, they're chasms. And in physics, a gap that large means something is missing from the picture. Scientists call this the hierarchy problem. It's not a minor puzzle, it's a crack in the foundation of everything we think we know about how the universe works. The equations that describe gravity and the equations that describe every other force refuse to line up. They point to a universe that shouldn't look the way it does. And yet here we are, holding refrigerator magnets, watching gravity lose over and over again. One proposed solution changes everything. Gravity is the only force in the universe that might be able to travel outside our reality. Every other force, light, magnetism, the nuclear forces, they're all locked into the 3 dimensions of space we know. But gravity could be slipping sideways, leaking into hidden extra dimensions that sit right next to ours, touching our universe at every point, yet completely invisible to everything we've ever built. If that's true, then the gravity we measure is only a fraction of gravity's full strength. The rest of it is somewhere we've never been and may never go. That idea sounds like it belongs in a movie. It doesn't. It comes from the highest levels of theoretical physics, and it has a machine dedicated to testing it. A machine 16 miles wide, buried 300 feet underground, running at temperatures colder than outer space. Scientists built it specifically to answer questions like this one. The hierarchy problem didn't start with particle colliders or string theory. It started with a refrigerator magnet. One small, embarrassing observation that revealed a gap in our understanding of reality so large you could lose entire dimensions in it. And the strange part is, you might be able to, because if extra dimensions are real, and gravity is leaking into them right now, the consequences don't stop at a physics textbook rewrite. They reach all the way down to what space and time actually are, and whether the universe we can see is even close to the whole story. That machine underground was built to find out. Let's go inside it. Picture a tunnel wide enough to drive a car through, running in a perfect circle 16 miles around. Buried 300 feet beneath farmland and the outskirts of Geneva. Lit by fluorescent lights, lined with thousands of the most powerful magnets ever built, and running around its entire loop, invisible to the naked eye. Beams of protons moving at a speed so close to the speed of light that the difference is almost meaningless. That's the Large Hadron Collider, the largest and most powerful particle accelerator ever built. The numbers are hard to picture, so start with the size. 16 miles of tunnel in a ring. You could fit the island of Manhattan inside the loop and have room to spare. The tunnel crosses the border between France and Switzerland so many times that no one bothers to mark which country any given section is in. The protons traveling through it are not traveling fast. Fast doesn't cover it. They complete that 16-mile loop 11,000 times every second. At that speed, the particles are technically getting heavier. Einstein predicted this. When objects approach the speed of light, their mass increases. The protons inside the collider are about 7,000 times heavier while moving than they are at rest. Moving them in a circle at that speed requires magnetic force on a scale that sounds impossible. 9,300 superconducting magnets are arranged around the ring, each one designed to bend the particle beams with precision. These magnets can't run at room temperature. They operate at minus 456 degrees Fahrenheit. That is colder than the vacuum of deep space. A section of this tunnel running under Swiss farmland is the coldest large object in the known universe. Then the beams collide. Two beams run in opposite directions. When they cross at specific points along the ring, protons from one beam smash directly into protons from the other. The energy at the collision point reaches 13.6 tera electron volts, a number that means nothing by itself. In human terms, it means the temperature at the exact moment of impact climbs to hundreds of thousands of times hotter than the center of the sun. For one unimaginably brief instant, a tiny speck of space becomes the hottest point in the solar system. This happens billions of times per second. The collisions don't produce a flash or a sound. They produce particles. Dozens to hundreds of fragments spray out in every direction from each impact, moving at nearly the speed of light themselves. Those fragments are the data. Scientists built massive structures around the collision points to catch them, track them, and measure everything about them. The collider was built with a list of targets: find the Higgs boson, probe the Standard Model, search for dark matter, and look for any sign of physics that doesn't fit what we already know. Extra dimensions are on that list. Microscopic black holes are on that list. Every proton collision is a small, controlled explosion of pure energy, an echo of conditions that haven't existed since the first fractions of a second after the Big Bang. Scientists run the machine for months at a time, logging billions of collisions, hunting through the wreckage for the one event in a billion that points somewhere new. So far, the machine has found things no one expected, and some things that still have no explanation. The search for extra dimensions starts with a problem even stranger than the magnet. It starts with the question of why our universe has the number of dimensions it does, and what would happen if that number is wrong. Imagine you're an engineer designing the universe from scratch. You have four forces to work with: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Your job is to make them all play nicely together at every scale, from the size of a galaxy down to the inside of an atom. You run the math, everything lines up almost, then you hit gravity. Gravity is trillions upon trillions of times weaker than electromagnetism at the subatomic scale. You check the math again. The gap is real. It's enormous. And the standard equations offer no explanation for why it exists. Physicists call this the hierarchy problem. The word hierarchy here means a ranking. a structure where things are ordered. The problem is that the forces don't sit at similar levels. Gravity sits so far below the others that the difference strains the ability of numbers to describe it. Here's a way to feel it. If you scaled gravity up to match the strength of electromagnetism, you'd have to multiply it by a 1 followed by 36 zeros. That's not a rounding error. That's a sign that something is fundamentally different about how gravity works compared to everything else. For decades, physicists treated this as an unresolved puzzle. Annoying, but survivable. Then, two things happened. First, the mathematics of string theory revealed that the universe might contain far more dimensions than anyone assumed. Second, a group of physicists realized that extra dimensions could solve the hierarchy problem entirely. The logic goes like this. Gravity appears weak because it's spreading out into directions we can't detect. Every other force is locked into our 3 dimensions of space. Gravity bleeds outward into extra dimensions, and by the time it reaches our world, its strength has been diluted across a much larger space. What we measure as weak gravity is gravity operating at full strength somewhere we can't see. It's like a speaker pumping sound through an enormous open field. If you're standing next to it, the music is deafening. Walk far enough away, and you can barely hear it. The speaker is just as loud. The sound has simply spread out over more space. Gravity might work the same way, except the space it's spreading into is hidden from us. This idea shifted the hierarchy problem from a puzzle into a target. If gravity leaks into extra dimensions, then those dimensions should leave fingerprints. Measurable ones. The fingerprints might show up as energy that disappears in a particle collision, or as heavier versions of known particles, or as microscopic black holes that flash into existence and vanish before they can be studied directly. All of those fingerprints are things the collider could find. The hierarchy problem also carries a personal dimension, for lack of a better word. If you're made of atoms, and atoms are held together by forces that are all roughly the same strength except gravity, then the fact that gravity is so different shapes everything about your physical existence. The size of stars, the length of a human lifetime, the distance between galaxies. These are all consequences of gravity's weakness. Fix gravity's weakness, and you change the blueprint of everything. Scientists built the most expensive scientific machine in history partly to chase this down, and the theory they keep returning to makes a demand that sounds almost absurd. The universe has more dimensions than you think. Here's the problem. Physics has 2 rulebooks. The first rulebook covers the big stuff. Planets, stars, galaxies, the bending of space around massive objects. It's called general relativity, and it works perfectly. Every prediction it makes checks out. Spacecraft navigation, GPS satellites, gravitational wave detection, all of it runs on Einstein's equations, and the equations never miss. The second rulebook covers the tiny stuff. Atoms, electrons, quarks, photons. It's called quantum mechanics, and it works perfectly too. Every experiment ever run at the subatomic scale confirms it. Modern computers, lasers, medical imaging equipment, all of it depends on quantum mechanics, and quantum mechanics never fails. 2 perfect rulebooks. 1 problem. They contradict each other. When you try to apply quantum mechanics to gravity, the math falls apart. Numbers go to infinity where they shouldn't. Predictions become nonsense. It's like 2 calculators that each give correct answers separately, but when you plug them into each other, one of them catches fire. For the last century, the biggest project in theoretical physics has been finding one rulebook that covers everything. A theory that works at the scale of galaxies and at the scale of quarks without breaking down in the middle. String theory is the leading candidate. The core idea is this. Instead of treating particles as tiny points, treat them as tiny vibrating loops of energy. Different vibrations produce different particles. An electron vibrates one way, a photon vibrates another way, gravity's carrier particle vibrates in its own pattern. On paper, this cleans up the contradictions between general relativity and quantum mechanics. But the math only works under a specific condition. The universe has to have 10 dimensions. 3 dimensions of space we know, 1 dimension of time, and 6 more dimensions of space that must exist for the string equations to stay coherent. Remove any of those 6, and the math produces answers that can't describe reality. The 10-dimensional structure isn't a bonus feature of the theory. It's a requirement. The theory doesn't function without it. That puts string theory in a strange position. It makes a clear, falsifiable prediction: 6 dimensions of space exist beyond the 3 we experience. If any experiment ever proves that wrong definitively, string theory collapses. If any experiment finds evidence of those hidden dimensions, string theory gains its strongest support ever. The prediction also raises an obvious question. If 6 extra dimensions exist, where are they? Humans have built extremely precise instruments over centuries of science. We've measured distances down to billionths of a meter. We've tracked individual atoms. If 6 extra dimensions of space are woven into the fabric of reality, why hasn't anything ever detected them? The answer string theory gives is that the dimensions are there, but they're too small to find with any tool built so far. They didn't disappear. They folded. Right after the Big Bang, when the universe was unimaginably hot and dense, something happened to those 6 dimensions. And what happened to them is one of the strangest ideas in all of physics. The Big Bang didn't just create matter and energy, it created space itself. In the first fractions of a second, the universe expanded from something smaller than a proton into a structure that already contained the seeds of everything that would ever exist. Space stretched outward in every direction. But according to string theory, it didn't stretch equally in every direction. 3 dimensions of space expanded into the enormous universe we live in today. The other 6 dimensions did something different. They folded in on themselves, curling up into shapes so small that no instrument has ever come close to detecting them. Physicists call this compactification. Picture a garden hose stretched across a football field. From far away, it looks like a line, one-dimensional. You can see it running from one end zone to the other, and that's it. But walk up close and look at the hose itself. It has a circular cross-section. A second dimension wraps around it. From a distance, that circular dimension is invisible. It's too small to register. String theory says space works the same way. Every point in the 3 dimensions we can see also has 6 extra dimensions looped around it in shapes called Calabi-Yau manifolds. These shapes are mathematically complex, with hundreds of possible configurations. Each configuration would produce a universe with slightly different physical laws. The shape of the hidden dimensions might determine why the forces have the strengths they do, why particles have the masses they do, and possibly why gravity is so much weaker than everything else. The size of these curled-up dimensions matters enormously. Most string theory models place them near the Planck length, a scale so small that putting it in context requires a strange comparison. If you shrunk an atom down to the size of the known universe, the Planck length would still be smaller than the atom you started with. Building an instrument to probe that scale directly would require an accelerator the size of a galaxy. But here's the key tension. Some theoretical models argue the extra dimensions don't have to be that small. They could be much larger, relatively speaking. Instead of existing at the Planck length, they might extend up to a millimeter or so in size. That's still invisible to the naked eye. But it's enormous compared to the Planck scale, and it falls within the range that a particle accelerator could potentially probe. If extra dimensions are that large, gravity's weakness is immediately explained. gravity spreads across those dimensions. Its strength gets divided over a much larger space before it reaches us. The question is, which version is right? Tiny and forever out of reach, or large enough to leave a detectable signal? Scientists at the Collider ran experiments to test exactly this. They looked at how gravity behaves at distances smaller than a millimeter. If extra dimensions exist at that scale, gravity should start acting stronger than predicted at very short range. The force should spike in a way that breaks from the normal pattern. No spike appeared down to scales tested so far. That rules out the largest possible extra dimensions. But it leaves open a wide range of smaller sizes, any one of which could still solve the hierarchy problem. And that range is exactly where the particle collision data starts to get strange. Every force you've ever felt comes from your universe. When light hits your eyes, that's electromagnetism. When you feel heat, that's energy carried by photons. When a magnet pulls metal across a table, that's electromagnetic force acting through space. All of it, every sensation and every interaction, happens within the 3 dimensions of space we live in. Physicists have a name for our universe in this picture. They call it a brane, short for membrane. The idea is that our 3-dimensional universe is a surface, like the skin of an enormous bubble, floating inside a much larger space that has extra dimensions. That larger space is called the bulk. Here's the picture. Imagine 2 giant sheets of paper floating parallel to each other inside a room. Each sheet is a 2-dimensional surface. The room around them is the 3-dimensional bulk. Beings living on one sheet can move forward, backward, left, and right. But they can't jump off the surface into the room itself. They're stuck on their brane. We are those beings. We live on a 3-dimensional brane. The bulk around us might have 4, 5, or 6 extra dimensions of space. We can't move through them. We can't see into them. We can't even detect them directly. Every particle we know follows this rule. Electrons are brane particles. Photons are brane particles. Quarks are brane particles. The equations of particle physics describe these particles as fundamentally attached to the brane surface. They propagate through our 3 dimensions with no ability to cross into the bulk. But one particle might break that rule. One force has the unique property of being able to leave our brane and travel through the bulk. That force is gravity. Gravity's carrier particle, the graviton, is predicted by theory to be free from the brane. While every other particle bounces around on our surface, the graviton can slip off the edge and travel freely through the bulk. This is why gravity appears weak to us. Most of its actual strength is operating in the bulk, in dimensions we cannot access, and only a fraction makes it back to our brane where we can measure it. The brane world idea comes in several versions. The simplest version has 1 extra dimension. More complex versions have multiple extra dimensions in the bulk. In some versions, the bulk contains other branes, other surfaces, other universes. Running parallel to ours, separated by a gap in the extra dimensions so small it would make the diameter of a proton look enormous. Those other branes would be invisible to us. We couldn't shine a flashlight at them and see a reflection. We couldn't send a radio signal across. Every tool we have uses electromagnetic radiation in some form, and electromagnetic radiation is locked to our brane. But gravity could cross that gap, and if a nearby brane exists with mass on it, we'd feel its gravity. We'd be attracted to something we could never see, locate, or understand. A gravitational pull from another universe. Some physicists think this might explain dark matter. An invisible source of gravity pulling on our galaxy from just outside our brane. That idea alone is enough to make the next discovery feel urgent. Because if branes are real, what gets created when 2 of them collide? Every force in the universe comes with a carrier particle. Electromagnetism is carried by the photon. The photon zips between charged particles and transfers the electromagnetic force between them. It moves through empty space at the speed of light, which makes sense because light itself is a photon. The weak nuclear force has its own carrier particles. So does the strong nuclear force. These particles are all firmly planted in our three-dimensional world. They travel through our space and interact with matter on our brain. Gravity's carrier particle is called the graviton. It has never been directly detected. Detecting a single graviton would require a detector so large and sensitive, it would effectively need to be the size of Jupiter. But the graviton is predicted to exist by the mathematics of both general relativity and string theory. And its predicted behavior is unlike any other carrier particle. The graviton is a closed loop. The other force carriers are open strings, meaning they have two ends, and those ends are attached to the brain. An open string can vibrate through the bulk, but its endpoints stay anchored to our three-dimensional surface. That attachment is why photons and other force carriers are locked to our brain. Their endpoints can't leave. The graviton is a closed loop with no endpoints. Nothing anchors it to the brain. It can propagate freely in any direction, including straight out through the bulk into extra dimensions. When gravity acts between two objects in our universe, most of the gravitons carrying that force immediately wander off into the bulk. Only the ones that happen to curve back around to our brain contribute to the gravity we measure. This is a testable prediction. If gravitons regularly escape into the bulk, then certain particle collisions at the collider should produce a measurable energy imbalance. Two protons smashed together release a spray of particles in all directions, and the total momentum of those particles should balance out. Physics requires it. Momentum is conserved in every collision. If the momenta don't balance, something invisible carried the missing momentum away. And the only candidate is a graviton escaping into a hidden dimension. Scientists call this signature missing transverse energy. Transverse means sideways, crossing the beam path. When the detectors measure all the particles flying outward from a collision and find that the ledger doesn't add up, that imbalance points at something that left without saying goodbye. The challenge is distinguishing a real missing energy signal from background noise. Billions of collisions happen every second. Most produce known particles with predictable patterns. Sorting through that enormous volume of data to find the one event where momentum genuinely vanished rather than just going undetected requires algorithms that have to be almost impossibly precise. Scientists have been running this search at the collider for years. They've established that if gravitons are escaping, the extra dimensions they're escaping into must be smaller than what the earliest data runs could detect. Each new run at higher energy squeezes the possible size range tighter. But the search has produced something the team didn't fully expect. A handful of events where the energy accounting comes up short in ways that are hard to explain within the standard model. Hard to explain isn't the same as impossible to explain. But hard to explain is exactly the kind of signal that makes physicists run the experiment again at higher energy to see if the gap gets larger. In 2008, physicists powered on the collider for the first time. The goal list was long. Find the Higgs boson, probe the limits of the standard model, look for dark matter. And somewhere on that list, tucked between the known objectives and the speculative ones, hunt for the graviton. Finding the graviton would be the single most important discovery in the history of physics. A confirmed graviton sighting would unify the two competing rulebooks. It would prove gravity works by the same quantum rules as every other force. It would open the door to a complete theory of everything. So, why hasn't it been found? Because finding the graviton is almost impossibly hard. Every other fundamental particle was discovered by watching what it does in a detector. Photons leave tracks of electromagnetic energy. Electrons curve in magnetic fields. Quarks appear in pairs or triplets, bound together by gluons. Each particle has a signature, a fingerprint it leaves in the detector material. The graviton leaves nothing. If a graviton is produced in a collision and immediately escapes into a bulk dimension, it carries energy and momentum out of the detector without triggering a single sensor. It's the particle physics equivalent of a ghost. You can't catch it, but you might be able to see the outline of where it was. The outline is the missing energy signature. Scientists look at the total energy coming out of a collision and compare it to the total energy that went in. If those numbers match, nothing strange happened. If the outgoing energy is less than the incoming energy, something left. The missing portion is the ghost's shadow. The problem is that neutrinos do this too. Neutrinos are real, known particles that interact so weakly with matter that they sail straight through the detectors without leaving a trace. A collision that produces neutrinos will show the same kind of energy imbalance. Distinguishing a graviton escape from a neutrino escape requires statistical analysis of thousands of similar events, comparing the exact patterns of the missing energy to models of what neutrinos should produce. If the missing energy events cluster in a pattern that matches the neutrino model, scientists move on. If the clustering looks different, like the particles are being produced at a different rate or at different energy levels than neutrinos would predict, that's the signal. That's the graviton fingerprint. So far, the data hasn't produced a clear graviton fingerprint. Every anomalous event has found an explanation that doesn't require extra dimensions. But the searches have set tight boundaries. Scientists now know that if gravitons are escaping into extra dimensions, those dimensions must be smaller than a specific scale, and the gravitons must be carrying energy at a level the current machine hasn't fully probed. The next round of collisions runs at higher energy. The detectors are more sensitive. The algorithms processing the data are more refined. Every run at higher energy is another push toward the boundary where known physics ends and the unknown begins. And right at that boundary, a different kind of event might appear. One that doesn't just hint at something leaving. One that produces evidence of something briefly existing before it vanishes. A black hole smaller than a proton that lives for a trillionth of a second and then explodes. Physics is obsessed with balance. Every force has an equal and opposite reaction. Every particle produced in a collision has a partner that balances its charge, spin, and momentum. The universe keeps its own books, and those books must always add up. This isn't a preference. It's a law. Every experiment ever conducted has confirmed it. Momentum is conserved. Energy is conserved. The ledger always balances. So when the ledger doesn't balance, something extraordinary has happened. Scientists at the collider measure every collision with near-perfect precision. Two beams of protons moving in opposite directions slam into each other at the center of a detector the size of a 5-story building. The collision sprays particles outward. Detectors covering every angle catch those particles and record their energy, their direction, and their identity. The data arrives at processing centers at a rate that would fill 100,000 hard drives per year. From all that data, scientists calculate the total momentum of the particles after the collision. Physics requires that momentum to match the momentum that went in. The proton beams move in opposite directions, so the total momentum across the beam axis is 0. That means every collision should produce a spray of particles that collectively add up to 0 net momentum as well. When a collision produces a strong, lopsided spray, where lots of particles shoot off in one direction and almost nothing balances on the other side, the imbalance points at something invisible. That invisible something carried away the missing momentum. Scientists call this signal a monojet event, because the detector sees one jet of particles on one side and a hole where the balance should be. Monojet events happen. Some of them come from neutrinos, which are known and expected, but some monojet events at high energy look statistically different from what neutrino production should generate. The rate is slightly off, the energy distribution is slightly off. These are small differences, but in particle physics, small statistical differences are exactly how every major discovery started. The Higgs boson wasn't discovered with one single obvious event. It accumulated over months of data analysis, as a small statistical bump grew more and more significant against the background noise. Extra dimension signals would work the same way. A pattern of anomalous monojet events, building steadily across millions of collisions until the statistics rule out every alternative explanation. The current data has produced events that are unusual enough to keep the search active. The missing energy signatures haven't crossed the threshold scientists require to call it a discovery. That threshold requires the signal to be statistically strong enough that the probability of it being a random fluctuation drops below 1 in 3.5 million. Scientists haven't crossed that line yet for extra dimensions, but the search is tightening. And here's what makes the next round of data feel different from any previous run. The energy level has increased, and at higher energies, the collider might start producing something that leaves far more than just missing energy as its signature. It might start producing the most extreme objects in the universe, compressed into a space smaller than an atom. And when one of those objects forms, it doesn't quietly disappear. It explodes. A black hole the size of a city has the mass of a star. It warps space-time around it so severely that nothing, not light, not radiation, nothing at all, escapes once it crosses the event horizon. It consumes matter and grows. It persists for billions of years. If one appeared near our solar system, Earth would be destroyed before we finished our next sentence. The black holes the collider might create are nothing like that. These are quantum black holes. Microscopic, so small that they make an atom look enormous. If one formed inside the detector, it would contain roughly the same total energy as 2 colliding protons, compressed into a space many times smaller than a proton itself. The mass is equivalent to a few mosquitoes. The gravitational pull at that scale, even for a genuine black hole, is negligibly small. These objects would pose no threat. The physics is clear on that. But they would be scientifically staggering. Extra dimensions change the rules for black hole formation. In normal 3-dimensional space, creating a black hole requires compressing an amount of mass equivalent to a small mountain into a region the size of a proton. The collider can't come close to that. But if extra dimensions exist, gravity gets much stronger at small distances than it does in normal 3-dimensional space. The threshold for black hole formation drops dramatically. Suddenly, the energy in 2 colliding protons might be enough. If a microscopic black hole forms during a collision, it exists for roughly 1/10 of a trillionth of a second. In that sliver of time, it decays through a process first described mathematically by Stephen Hawking. The process is called Hawking radiation. Hawking's calculation showed that black holes aren't perfectly black. At their event horizons, quantum effects allow pairs of particles to form spontaneously. One particle falls in, one escapes. For enormous black holes, this process takes longer than the age of the universe. For a microscopic black hole the size of a particle collision, the evaporation is nearly instantaneous. The evaporation produces a burst of particles, dozens of them, radiating outward in all directions from a single point. This burst is specific. The type and distribution of particles it produces follow a pattern based on the temperature of the evaporating black hole. Hawking's equations predict exactly what that pattern should look like. If a collision produced this specific burst pattern, it wouldn't just be unusual, it would be unmistakable. Every existing standard model process has been modeled. None of them produce this exact spray of particles at this ratio and at this energy level. The burst would stand out against the background like a firework going off in a library. That's what scientists are looking for. They've built detection systems specifically to catch this pattern. Every time a collision event produces an unusually high multiplicity of particles, meaning an unusually large number of particles from a single point, that event gets flagged and studied. The flagged events so far have all been explained by known processes, but the collider hasn't reached the energy level where theoretical models predict black hole production becomes likely. That energy level is coming closer with each upgrade, and the second that burst pattern appears, it wouldn't just prove microscopic black holes exist, it would confirm extra dimensions in a single stroke. Stephen Hawking figured something out in 1974 that bothered him for years after he did it. He sat down to mathematically describe what happens right at the edge of a black hole, where the event horizon meets the quantum world. He applied the rules of quantum mechanics to the boundary of a region of warped spacetime. The answer his math returned surprised him. Black holes radiate. They emit particles, and over time they lose mass and eventually disappear completely. This was a shock. Black holes were supposed to be the ultimate one-way street. Matter falls in and never comes out. Hawking's calculation said that wasn't fully correct. At the quantum level, the event horizon produces a slow, steady trickle of particles that carry energy away from the black hole. For a black hole the size of a mountain, this process takes longer than the current age of the universe. The radiation is too weak to measure with any instrument ever built. But for a microscopic black hole, the mass of a few particles, the math changes entirely. The temperature of Hawking radiation scales inversely with the mass of the black hole. Smaller black hole, higher temperature, faster evaporation. A quantum black hole the size produced in a particle collision would have a temperature billions of times higher than the surface of the Sun. At that temperature, it would evaporate completely in a time so short it would make a nanosecond look like an era. The evaporation doesn't produce just one type of particle, it produces a democratic mix. Quarks, gluons, photons, electrons, and their antiparticles all come flying out in proportions tied to the temperature of the black hole. Hawking's equations give exact predictions for what that mix should look like. Scientists use this as a detection blueprint. When they run simulations of what a microscopic black hole evaporation event should look like in their detector, they get a very specific picture. Many particles, radiating outward roughly equally in all directions, with an energy distribution that follows a thermal curve, meaning the particles spread across a wide range of energies in a specific statistical pattern. The standard model produces events that roughly resemble this sometimes, but they fail to match the precise thermal curve. A real Hawking burst would produce a cleaner distribution. More particles. Wider spread. A distinctive flatness in the energy spectrum compared to the chaotic sprays that come from ordinary quark collisions. The detector algorithms are programmed to flag events that hit these criteria. Every collider run generates billions of collisions. Algorithms sort through them at speeds no human team could match, scoring each event against the Hawking evaporation template. Events that score above a threshold go into a separate dataset for human review. Over the years of collider operation, a small number of anomalous high multiplicity events have made it into that reviewed dataset. None cross the threshold of statistical certainty needed to announce a discovery. The threshold requires the probability of a false positive to be less than 1 in 3.5 million, and the current anomalies sit comfortably below that bar. What makes the next phase of data collection different is energy. Higher collision energy means higher mass quantum black holes. Higher mass means the Hawking temperature changes. A different temperature produces a different and more distinctive particle spectrum, one that's harder for background processors to mimic. Every upgrade to the machine is a new lens, and what those lenses are looking for next is even harder to imagine than a black hole smaller than a proton. When two protons collide at the center of the Large Hadron Collider, the event lasts less than 1/1,000,000,000th of a second. In that instant, the collision point becomes the hottest location in the solar system. Energy converts into particles, particles spray outward at nearly the speed of light, and a machine the size of a 5-story building, weighing more than 14,000 tons, tries to catch every single one of them. That machine is the compact muon solenoid. Physicists call it the CMS. The name is somewhat misleading. Compact compared to what? The CMS detector is 69 feet long, 50 feet wide, and 50 feet tall. It weighs more than the Eiffel Tower. Getting it underground required taking it apart into 15 massive sections, lowering each section through a specially constructed shaft, and rebuilding the entire structure 300 feet below the surface. The design is built around a principle that sounds simple, but required decades of engineering to achieve. You want to measure everything about every particle that comes out of a collision: charge, energy, direction, mass, and identity. To do that, you build the detector in layers, like an onion, and each layer catches something different. The innermost layer, closest to the collision point, is a silicon tracker. It contains 60 million individual detection channels. When a charged particle passes through, it leaves a tiny electrical signal. Reconstructing the path from all those signals tells scientists the particle's trajectory and momentum. The next layer is the electromagnetic calorimeter. It's a crystal structure that stops electrons and photons cold, measuring their energy precisely. Particles that punch through that layer hit the hadronic calorimeter, a dense structure designed to absorb the heavier particles called hadrons. Further out still is the solenoid magnet itself, a superconducting coil that generates a magnetic field 4 times stronger than a hospital MRI scanner. Charged particles curve in that field, and the degree of curvature reveals their momentum. The outermost layer handles muons. Muons are heavy cousins of the electron that pass through everything else in the detector without stopping. Special detectors around the outside of the structure catch them by measuring the ionization trails they leave behind. All of this runs simultaneously across billions of collision events per second. The raw data volume is so enormous that the detector's own processing systems discard most of it on the spot. They run a real-time filter that keeps only the most interesting events, roughly 100 out of every 40 million. The selected events are then processed by a global computing network spread across 170 sites and 42 countries. The entire system operates with the goal of missing nothing. An extra dimension event, a Hawking burst, a graviton escape, these are all needles in a data haystack of incomprehensible scale. The CMS was built to find those needles by being physically, computationally, and statistically capable of examining every piece of hay. On the opposite side of the collider ring, 16 miles away, sits a second detector built with a different design approach, specifically to cross-check everything the CMS finds. Because in physics, a discovery made by one detector that the other can't confirm isn't a discovery, it's a question. The Atlas detector sits at a different collision point, 16 miles from the CMS, on the opposite side of the ring. Atlas stands for a toroidal Large Hadron Collider apparatus. It's the largest particle detector ever built, 146 feet long, 82 feet tall and wide. The structure is enormous enough that you could stack 5 school buses on top of each other inside its central cavity and still have headroom. Unlike the CMS, which uses a single central solenoid magnet, Atlas uses a complex system of toroidal magnets, large ring-shaped coils arranged to create magnetic fields through the full volume of the detector in a different geometry. The design difference is deliberate. 2 detectors that work by the exact same method might share the same blind spots. If Atlas and CMS both see the same anomalous signal using different technologies and different magnetic field geometries, That agreement is extremely strong evidence that the signal is real rather than an artifact of how one particular machine works. Atlas and CMS operate like two completely independent scientific teams running the same experiment simultaneously, analyzing the same collisions from the same collision point, and comparing notes afterward. When the Higgs boson was discovered in 2012, both detectors announced the discovery on the same day. Their datasets were analyzed separately. Their statistical results agreed. That double confirmation is what made the announcement definitive. A single detector seeing a statistical bump is suggestive. Two independent detectors seeing the same bump at the same energy is a discovery. The same logic applies to extra dimensions. Any missing energy signal, any Hawking burst pattern, any anomalous particle spectrum would need to appear in both datasets before it could be taken seriously as evidence of new physics. Atlas has run searches for extra dimensions using the missing energy approach. It has analyzed monojet events, multi-jet events, and high multiplicity events, specifically looking for the signatures associated with graviton production, Kaluza-Klein particles, and microscopic black holes. The results to date have set boundaries, they've ruled out certain parameter ranges, they've confirmed that if extra dimensions exist, certain sizes and certain models don't fit the current data. What Atlas has also done is flag a small set of events that don't have comfortable standard model explanations. These events sit at the edge of the detector's energy reach, where new physics would be hardest to distinguish from statistical noise. The upcoming high luminosity upgrade to the collider will increase the number of collisions per second dramatically. Both Atlas and CMS will collect more data in a single year than they've collected over the entire history of the collider combined. Every collision is a new data point. More data means tighter statistical analysis. And tighter analysis means that any signal hiding just below the current detection threshold either rises clearly above the noise or gets ruled out entirely. That upgrade changes everything about what's knowable. But even before any new particle is found, two scientists from a century ago already pointed physics directly at extra dimensions. They did it with a pencil, paper, and an idea so strange that it was dismissed for decades. The Large Hadron Collider exists at two opposite extremes of temperature simultaneously, and both extremes are required for the machine to work. Start with the cold. The proton beams travel through a vacuum tube surrounded by superconducting magnets. These magnets need to carry enormous electrical currents to generate the magnetic fields that bend and focus the beams. Ordinary copper wire at room temperature has electrical resistance. Run a huge current through it, and it heats up and loses energy. To eliminate that resistance entirely, the magnets use superconducting cables made of a niobium titanium alloy. Superconductivity requires the material to be cooled below a critical temperature. For these magnets, that temperature is achieved using liquid helium. The operating temperature of the magnet system is minus 456 degrees Fahrenheit. For comparison, the coldest recorded temperature in deep space, in the Boomerang Nebula, reaches minus 458 degrees Fahrenheit. The collider's magnet system is essentially the same temperature as the coldest known region of the universe. 9,300 of these magnets run the full 16-mile circumference of the machine. Each one must be kept at that extreme temperature continuously during operation. The cooling infrastructure alone is one of the most complex cryogenic systems ever built. Now consider the heat. When two proton beams collide at 13.6 tera electron volts of combined energy, the collision point briefly reaches a temperature measured in the trillions of degrees, hundreds of thousands of times hotter than the center of the sun, hotter than the conditions that exist anywhere in the observable universe right now. Outside of certain extreme astrophysical events, this temperature spike exists in a region smaller than a proton and lasts for less than a trillionth of a second. But in that instant, the energy density recreates conditions that haven't existed since the universe was a fraction of a second old. The quark-gluon plasma, the primordial soup of unbound quarks that filled the universe before protons and neutrons formed, appears briefly in the collision debris. The contrast is almost impossible to visualize. The coldest large structure in the known universe, running 16 miles of superconducting tunnel, exists specifically to create the hottest points in the solar system billions of times per second. Both extremes are non-negotiable. Without the cold, the magnets fail and the beams can't be steered. Without the extreme heat, the collision energy falls short of the threshold needed to probe new physics. The machine lives at the intersection of these two conditions, and engineers maintain both around the clock. A single magnet quench, a sudden loss of superconductivity, releases energy equivalent to a small explosion and can halt operations for days while repairs are made. The engineers who run this machine have spent decades learning to work at the edge of what matter can do. And what the matter does at those extremes is reveal things that don't exist anywhere else, including phenomena that two physicists working in the 1920s predicted with pencil and paper long before any of this was buildable. In 1921, a mathematician named Theodor Kaluza sat in his study in Germany and wrote a letter to Albert Einstein. The letter contained a set of equations. Kaluza had been working with Einstein's general relativity equations, the ones that describe gravity as the curving of space and time around massive objects. He tried something strange. He added one extra dimension to the equations. A fifth spatial dimension, beyond the three we experience. When he ran the math, something happened that he didn't expect. The equations naturally produced a second set of field equations alongside the gravity equations. The second set described electromagnetism perfectly. By adding one invisible dimension, Kaluza had accidentally unified gravity and electromagnetism in a single mathematical framework. Einstein took 5 weeks to respond. Then he wrote back enthusiastically, calling the idea beautiful and striking. He spent the next few years trying to validate it himself. But there was an obvious problem. If a fifth dimension of space exists, where is it? Humans have been navigating three-dimensional space for our entire history. We've built instruments that measure space with extraordinary precision. Nothing has ever revealed a fourth direction. 5 years later, in 1926, a Swedish physicist named Oskar Klein answered that problem. Klein proposed that the fifth dimension wasn't stretched out like the other three. It was curled up, looped back on itself into a tiny circle. So small that no instrument of that era, or any era since, could detect it directly. The dimension was there, wrapped around every point in space, but at a scale so microscopic it was functionally invisible. The combined idea became known as Kaluza-Klein theory. It was remarkable for its time. A century before string theory demanded 10 dimensions, before the hierarchy problem became a central challenge in physics, two physicists working independently had already proposed that hidden spatial dimensions were the key to unifying the fundamental forces. The theory fell out of fashion for decades. Physics moved forward with quantum mechanics and quantum field theory, and those frameworks didn't immediately require extra dimensions. Kaluza-Klein theory got filed away as a beautiful but speculative idea that couldn't be tested. Then, string theory arrived and demanded 10 dimensions. Suddenly, the curled-up dimension that Klein had described in 1926 became a template. The compactification mechanism string theory relies on is a direct extension of Klein's insight. The mathematics evolved enormously, but the core idea that dimensions could curl up and hide at tiny scales came from Klein's pencil and paper work done a century ago. And Kaluza-Klein theory had one more prediction that turned out to be directly testable by modern particle accelerators. If particles travel through these looped hidden dimensions, they pick up extra momentum from the loop structure. That momentum appears in our three-dimensional world as extra mass. Every known particle should have a series of heavier copies stacked at specific mass intervals if hidden dimensions exist. These copies are called Kaluza-Klein recurrences. And finding one would be proof, not a hint. Proof the question is what a Kaluza-Klein particle actually looks like when it shows up in a detector. And the answer points at a particle we've already measured very precisely. When a particle travels around a tiny loop dimension, the loop changes it. Think of spinning a ball on a rope. The ball has speed. It has momentum. All of that momentum is real, but it's directed in a circle. From far away, someone watching the whole system might not see the circular path clearly. They'd just see an object that seems to have extra energy tied up inside it somehow. That's roughly what happens to a particle navigating a compactified extra dimension. The particle moves around the loop at a speed determined by the size of the loop. That circular momentum is real. It contributes to the particle's total energy. And in Einstein's framework, energy and mass are interchangeable. So the particle, as seen from our three-dimensional perspective, appears to have more mass than its normal version. The heavier version is a Kaluza-Klein recurrence, a particle that is identical to its known counterpart in charge, spin, and all other properties, but carries significantly more mass because it's simultaneously vibrating through a hidden dimension. The mass increase isn't random, it scales with the size of the hidden dimension. A smaller loop produces higher mass copies because the particle has to move faster to complete the loop, gaining more circular momentum. A larger loop produces copies with lower extra mass. By measuring the mass gap between a known particle and its Kaluza-Klein copy, scientists could calculate exactly how large the hidden dimension is. The particle physicists focus on most is the Z boson. The Z boson is a well-understood carrier of the weak nuclear force. Scientists have measured its properties with great precision. Its mass is known to many decimal places. If a Kaluza-Klein version of the Z boson exists, it would look exactly like a Z boson in every quality except mass. It would decay into the same pairs of particles. It would have the same charge and spin. It would just be much heavier. This is searchable, directly searchable. Particle collisions at high enough energy can produce Z bosons. If collisions at even higher energy start producing particles that decay like Z bosons but carry far more mass, the data would show a bump in the mass spectrum at the exact energy corresponding to the Kaluza-Klein version. Scientists search for these bumps in the mass spectrum constantly. The technique is called a resonance search. When a new particle exists at a specific mass, collisions that reach that energy level produce it more frequently, creating a visible spike in the production rate against a smooth background. No Kaluza-Klein resonance has been confirmed. The searchers have ruled out Kaluza-Klein particles up to certain mass values, pushing the boundary higher with each data run. Each ruled out mass range tells scientists that if the hidden dimension exists, it's smaller than the calculation for that mass range implies. The current lower limit on Kaluza-Klein particle masses sits in the range where the collider is still actively collecting data. The boundary hasn't been resolved, it's been pushed. The upcoming data collection phases will extend the search to higher masses. A confirmed resonance at any mass would be the discovery of the century. But ruling out increasingly high masses also has value, because it eventually starts to close off the theoretical parameter space. And when the parameter space closes off, physics has to either upgrade its instruments or upgrade its ideas. One candidate for the next testable idea is a Z boson copy so heavy it would require rethinking what forces look like at the highest energies. And that idea connects directly to a scale of physics so extreme it has its own name. In 1983, a team at CERN detected the Z boson for the first time. It was a triumph that capped decades of theoretical work. The Z boson was the missing piece that confirmed the Standard Model's description of the weak nuclear force. Its discovery earned 2 physicists a Nobel Prize. Since then, the Z boson has been measured with extraordinary care. Its mass is known precisely. Its decay modes are catalogued completely. Millions of Z bosons have been produced at particle accelerators and studied in detail. Scientists know exactly what a Z boson looks like in a detector. So here's the scenario. You're sifting through collision data at the collider. You see a particle decay into an electron and its antiparticle, a positron. This is a classic Z boson decay. You measure the combined energy of the electron and positron to figure out the mass of the parent particle. A normal Z boson registers at a specific mass every time, but this event shows a mass significantly higher, several times higher. The decay looks identical. The daughter particles are the same, only the mass is wrong. That's what a Kaluza-Klein recurrence of the Z boson would look like. A particle with the same electromagnetic fingerprint as a Z boson, but carrying extra mass that it picked up from vibrating through a hidden spatial dimension. The search for this heavy twin runs in parallel with the missing energy searches and the Hawking burst searches. It's called a dielectron or dilepton resonance search, because the signature is a pair of leptons, like an electron and a positron, with an unusually high combined mass. The collider has run this search across multiple datasets. Scientists look at the combined mass distribution of all lepton pairs produced in collisions. Under normal conditions, that distribution shows smooth curves with known peaks at the masses of known particles like the Z boson. If a Kaluza-Klein twin exists at some higher mass, it would show up as an extra bump riding on top of that smooth background. The searchers have produced some events at high mass that sit slightly above background expectations. None of these bumps has reached the statistical level needed for a discovery announcement. But none has disappeared completely after more data was collected either. Some persist at a low level across multiple data runs. In particle physics, a persistent small excess that refuses to go away is the most tantalizing kind of result. It could be a fluctuation. It could be a systematic error in the detector calibration. Or it could be the first edge of a real signal waiting for enough data to fully emerge. The dielectron search is considered one of the cleanest signatures in collider physics. The background processes are well understood. The detector response to electrons and positrons is extremely well characterized. A genuine excess in this channel is hard to explain away. When the high luminosity upgrade activates, the number of events in this channel will multiply dramatically. If the small persistent excesses are real signals, they'll grow into obvious peaks. If they're noise, they'll wash out against the larger dataset. Either way, a definitive answer is coming. And what that answer points to, whether it confirms a heavy Z-twin or rules it out completely, changes the next question physics has to ask. The next question involves a scale so extreme that the numbers themselves require a story to land. There is a distance so small that physics itself breaks down at its edge. It has a name. The Planck length, named after Max Planck, the physicist who first identified the fundamental constants that define it. The Planck length is calculated by combining 3 of the most basic numbers in physics: the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When you run those numbers together, you get a length of about 1.6 times 10 to the negative 35th meters. That number means nothing on its own. Here's a picture instead. Take a single proton. A proton is already unimaginably small. You could line up 1 trillion of them across the period at the end of a sentence. Now take that proton and imagine shrinking it down until it looks the size of the observable universe. At that scale, the Planck length would still be smaller than the proton you started with. At the Planck scale, quantum mechanics and gravity stop being separate rulebooks and start trying to describe the same thing. Space and time themselves lose their smooth, continuous character. They become foamy and chaotic at that scale, fluctuating wildly in ways that our current equations can't fully describe. Physics as we know it simply stops giving clean answers. String theory places the 6 curled-up extra dimensions at or near the Planck length. If that's correct, the dimensions are so small that even the collider, running at its maximum possible energy, would fall short of probing them directly by an enormous margin. Reaching the Planck scale directly would require an accelerator roughly the size of the Milky Way galaxy. That's not going to happen. But here's what makes the Planck scale a genuine target rather than just an abstract limit. The collider doesn't need to reach the Planck scale directly to find evidence of physics at that scale. Just as a geologist can learn about Earth's deep interior by studying seismic waves on the surface, particle physicists can look for ripple effects of Planck scale physics in the collision data produced at much lower energies. If extra dimensions exist at the Planck length, they should still leave statistical fingerprints in the data. Subtle deviations from the standard model predictions, tiny anomalies in particle production rates, small but measurable differences in how certain particles decay. These fingerprints appear at the energies the collider can reach, even if the underlying physics lives at a scale the collider can't directly touch. The search for Planck scale signals is one of the more technically demanding analyses the collaboration runs. The expected signal is small, buried in background processes that produce similar-looking data. Finding it requires processing years of collision events and looking for deviations measured in fractions of a percent. But if Planck scale extra dimensions left no footprint at all at reachable energies, physics would need to wait indefinitely for a machine capable of reaching those scales directly. The encouraging part is that some theoretical models place extra dimensions much larger than the Planck scale. Enormously larger. And that brings up a question that reframes everything about how hidden dimensions are supposed to work. How big could a hidden dimension actually be and still be completely invisible to us? In 1998, 3 physicists published a paper that changed the conversation about extra dimensions entirely. Their names were Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali. Their proposal became known by the initials of their last names as the AD model. And the proposal was radical. They argued that extra dimensions don't have to be anywhere near the Planck length. They could be much, much larger. In the AD model, the hidden dimensions could be as large as a fraction of a millimeter across. To a human being, a millimeter is nearly invisible. To physics, a millimeter is an enormous distance at the subatomic scale. An extra dimension a millimeter wide is roughly 10 trillion times larger than the Planck length. The key to making this work is the structure of the brain world. In the AD model, all of the standard model particles and forces are locked to our brain. They can't explore the extra dimension. So even if the extra dimension is a millimeter wide, no experiment using electromagnetic signals, which means essentially all experiments in chemistry, biology, optics, or electronics, would ever detect it. The only force that could probe it is gravity. And here's the payoff. If gravity spreads across one or more large extra dimensions, its strength gets diluted over that extra volume. The actual fundamental strength of gravity could be enormous, comparable to the other forces. What we measure as weak gravity is just gravity spread thin across the extra dimensional volume. This completely solves the hierarchy problem without requiring any exotic fine-tuning of the equations. The AD model also makes a specific prediction about how gravity should behave at small distances. At distances larger than the size of the extra dimension, gravity follows the familiar inverse square law, weakening as distance squared. At distances smaller than the size of the extra dimension, gravity should deviate from that law and start following a steeper curve, growing stronger faster as distances shrink. Testing this requires measuring the gravitational force between two small objects separated by less than a millimeter. Several groups have run these experiments using small torsion balancers, precision instruments that detect tiny twists in suspended wires caused by gravitational attraction. These experiments have probed gravity down to scales smaller than 1/10 of a millimeter. The inverse square law holds. No deviation has appeared. This rules out large extra dimensions at the millimeter scale, but it leaves open the possibility of extra dimensions at scales below the current measurement limit, which sits around 40 to 50 microns, roughly the width of a human hair. A dimension 40 microns wide. Still invisible. Still enormous compared to the Planck length. Still capable of solving the hierarchy problem, and still capable of leaving signals at particle colliders. The AD model keeps the hierarchy problem solution alive even after the millimeter scale tests came back empty. It just moved the target to a smaller size, and at smaller sizes, the collider becomes the primary tool for detection. But even if all these size scales are ruled out one by one, there's still a version of the extra dimension story that doesn't depend on size at all, and it changes what a hidden dimension might contain. Imagine you live inside a wall. The wall is 1 inch thick. You can move left, right, up, and down anywhere along the surface of the wall. You can't move through the wall itself because everything about your physical structure keeps you pinned to the surface. You eat, breathe, and think entirely within the wall's 2 dimensions. Now someone from outside asks you if you've ever detected the inch of thickness your wall has. You say no, because every tool you've built uses signals that travel along the surface. Every measurement you've made happens within the surface. The thickness is real. The 3rd dimension of the wall is real. You simply have no way to access it. That's our situation, scaled up. Every experiment in the history of science uses electromagnetic signals in some form. Light bounces off objects and enters our eyes. Radio waves carry data through the air. X-rays pass through tissue and expose film. The electrical signals in a computer are electromagnetic. The measurements in a particle detector track charged particles by the electromagnetic force they exert. All of these tools are locked to our brain. Electromagnetic signals propagate through our 3 dimensions of space and through time. They do not cross into extra dimensions. If a hidden dimension sits perpendicular to all 3 of our spatial dimensions, no electromagnetic signal can enter it, exit it, or even glance at it. It would be invisible by construction, not by coincidence. This is why the size of the extra dimension is almost secondary to its existence. Even a dimension as large as a football field would be completely undetectable to any human-built instrument that uses light, radio waves, sound, or any electromagnetic phenomenon. The only exception is gravity. And gravity is so weak at laboratory scales that measuring its behavior at the precision needed to detect a hidden dimension requires instruments balanced to detect forces smaller than the weight of a single bacterium. The torsion balance experiments that probe gravity at sub-millimeter distances operate at that level of precision. They measure gravitational attraction between small metal spheres separated by tiny distances, looking for any departure from the expected pattern. Running these experiments requires isolation from vibrations, temperature changes, and electromagnetic interference so complete that the labs are often located in basements with multiple layers of insulation. The same reasoning applies to particle detectors. The reason the collider can probe extra dimensions at all is specifically because gravity, and only gravity, can escape into them. Every signal the collider produces for every other type of physics involves electromagnetic force somewhere along the chain. Extra dimensions show up only through the gravitational channel. missing energy, Kaluza-Klein mass shifts, or Hawking burst patterns. That electromagnetic blindness also raises a genuinely strange possibility. Extra dimensions could contain structures, fields, even forces with no electromagnetic component at all. We would feel their gravity. We would feel nothing else. Physicists have a name for this kind of hidden sector, and what that sector might contain goes well beyond empty space. The question sounds almost philosophical. What's inside a dimension we can't enter? Physicists don't treat it as philosophy. They treat it as a real theoretical problem with real consequences. And the answer space is wider than most people realize. The simplest possibility is nothing. Extra dimensions could be geometrically real, curled up and compactified, carrying gravitational effects into our world, but otherwise completely empty. No matter, no fields, no structure beyond the mathematical geometry of the space itself. This would still solve the hierarchy problem and still explain gravity's weakness, but the dimensions would be dark and featureless. The second possibility is richer and stranger. Hidden dimensions could contain their own physical laws. The standard model particles that make up our world, the quarks, electrons, and force carriers, are locked to our brain. But the bulk could support other types of particles that only exist in the extra-dimensional space. These particles would have their own interactions, their own forces, their own rules. They would form a dark sector, a parallel layer of physics running alongside ours, invisible to every tool we have except one. Gravity crosses the boundary. Any matter in the bulk, on a nearby brain, or floating in the dimensional space between brains, would attract our matter gravitationally. We'd feel its pull without seeing it, touching it, or interacting with it in any other way. This is exactly how dark matter behaves. Dark matter is one of the most confirmed puzzles in cosmology. Galaxies rotate faster than the visible matter in them can explain. The cosmic web of galaxy filaments forms structures too large to be explained by ordinary matter alone. Gravitational lensing around galaxy clusters shows more mass than any telescope can see. Something real and massive is there. It just doesn't emit, absorb, or scatter light in any measurable amount. One theoretical explanation is that dark matter particles are ordinary matter, similar in kind to what we're made of, but living on a nearby brain separated from ours by a tiny gap in an extra dimension. Those particles are electromagnetically invisible to us because their electromagnetic force is contained on their own brain. But gravity, free to travel across the gap, makes their mass felt on our side. If this is correct, the dark matter that shapes every galaxy in the universe is matter on a surface parallel to ours, close enough to affect us gravitationally, separated by a distance smaller than any particle ever detected. This isn't the only dark matter hypothesis. There are others. But this one ties extra dimensions to one of the biggest mysteries in observational astronomy. And if dark matter is brain matter, then the galaxy you live in sits inside a gravitational landscape shaped partly by a universe you'll never see. A universe close enough to touch, if touching across dimensions was something that could happen. What happens when two brains get close enough that touching actually occurs is the subject of one of the most violent ideas in all of cosmology. Science doesn't only move forward by finding things. Sometimes it moves forward by eliminating possibilities. And the search for extra dimensions has eliminated a wide range of possibilities in a way that has actually made the remaining possibilities more precise and more testable. The process started with gravity measurements at small scales. When the AD model proposed that extra dimensions could be as large as a millimeter, the immediate test was to measure gravity at that range. Torsion balance labs ran the experiment. Gravity behaved exactly as expected. The inverse square law held. Extra dimensions at the millimeter scale were ruled out. The experiments were refined. Gravity was tested at shorter distances. Half a millimeter, a tenth of a millimeter, 50 microns, roughly the width of a human hair. The inverse square law continued to hold. Each new distance tested pushed the boundary on how large a hidden dimension could be while still being undetected. At the collider, the approach was different. Rather than measuring gravity directly, scientists searched for the particles and signals predicted by extra-dimensional models at specific size scales. Each model ties the size of the extra dimension to the energy at which its signatures should appear. Smaller dimensions require higher energy collisions to produce detectable signals. The collider tested models predicting Kaluza-Klein particles at lower masses first. Those particles didn't appear. The boundary was pushed higher. The same pattern repeated for missing energy searches. At each energy level tested, the data either found the signal or didn't. When the signal didn't appear, the model producing it was constrained. The allowed parameter space shrank. This is what scientific progress looks like in this field. A systematic narrowing of possibilities. Each ruled-out model tells theorists something real about the structure of the universe. If large extra dimensions at scale X don't produce signals at energy Y, then models requiring those parameters are eliminated. The remaining theoretical landscape has sharper edges. The constraints from both gravity tests and collider searches now combine to say something specific. If extra dimensions exist, they are smaller than about 40 microns, and their associated Kaluza-Klein particles are heavier than current collider searches have fully probed. The remaining allowed window sits at energies the upcoming high luminosity collider phase will reach. The window hasn't closed, it's been shaped. What makes this window scientifically important is what sits inside it. The models that survive the current constraints are exactly the models that the next phase of experiments can test. The ruling out process has done its job by clearing away everything that doesn't fit and leaving a specific testable target. Scientists know where to look. The machine is getting more powerful, and the datasets that will determine whether anything lives in that remaining window are being collected right now. Somewhere in the next several years of data, the question either resolves or pushes physics toward a completely different path, and the anomalies already present in the current data suggest the resolution might arrive sooner than anyone expected. Every large data set in physics contains anomalies, events that don't quite fit the expected pattern, spikes in the data that sit slightly higher than the background, deviations from predictions that appear in one run and need confirmation in the next. Most of them go away. More data arrives, the spike flattens, the deviation regresses to the mean, the anomaly gets classified as statistical noise, and the analysis moves on. Some of them don't go away. The collider's history of running contains a small set of anomalies that have persisted across multiple data-taking periods. They don't rise to the level of discovery. They hover in a region physicists describe carefully as intriguing, statistically significant enough that they can't be instantly dismissed, physically meaningful enough that multiple theoretical teams have published papers attempting to explain them. One class of anomalies involves specific decay patterns of particles containing a bottom quark. The standard model predicts these decays should happen at specific rates, producing specific ratios of daughter particles. For years, measurements showed small but consistent deviations from those predictions. The deviations pointed at the possibility of undiscovered particles interacting with the bottom quark family, nudging decay rates away from standard model expectations. These deviations fluctuated across multiple measurement cycles. Some shrunk as new data arrived, others persisted at a reduced level. The community debated whether they represented new physics or systematic measurement errors. The final verdict on several of these anomalies is still not fully settled, and new measurements continue to refine the picture. A second class of anomalies involves the production rates of certain particle pairs at high mass. When the collider produces pairs of particles at energies well above the known mass peaks, the rate should follow a smooth, predictable curve described by standard model calculations. In certain channels, the observed rate sits slightly above that curve at specific mass values. The excess forms a soft bump rather than a sharp peak, which makes it harder to interpret as a single new particle, but it also makes it harder to dismiss entirely. What connects these different anomalies and why they're relevant to the extra dimension search is that several theoretical models invoking hidden sectors, Kaluza-Klein particles, or extra-dimensional graviton effects predict exactly these kinds of broad, soft deviations. They don't predict sharp peaks like a new, ordinary particle would produce. They predict subtle distortions across a range of energies because the extra-dimensional effects spread across multiple mass scales. That makes the anomalies suggestive rather than definitive. A sharp peak would mean a single new particle with a specific mass. A broad soft excess means something more diffuse is influencing the distribution, potentially something spread across a hidden dimension rather than localized at one energy. The high luminosity data collection will resolve these. Either the soft excesses sharpen into real signals as statistics improve, or they fade as the increased sample size averages out the fluctuations. In physics, the distance between intriguing and confirmed can span years of work. But right now, the distance is closing. And closing faster than expected, because the next upgrade doesn't just collect more data, it changes what the machine can physically produce. In 2012, a team of thousands of physicists announced the discovery of the Higgs boson. The moment came after decades of searching. The Higgs boson was the last predicted piece of a theoretical framework called the Standard Model, and its detection completed the structure that had been built piece by piece since the 1960s. The announcement was celebrated as one of the greatest achievements in the history of science. Two of the physicists who originally predicted the Higgs boson's existence received the Nobel Prize in Physics the following year. And then physics got back to work, because the Standard Model's completion also clarified its limitations with brutal precision. The Standard Model describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force all fit inside it cleanly. The particles that carry these forces and the particles that make up matter are all accounted for and measured. The framework is internally consistent and extraordinarily well confirmed. Gravity is missing. The Standard Model has no description of gravity at the quantum level. This isn't a gap at the edges, it's a gap at the foundation. Gravity is the first force a person experiences in life, the thing that keeps them on the ground, and the Standard Model has nothing to say about how it works at the scale of particles. Dark matter is missing too. Roughly 27% of the universe's total mass and energy content is dark matter. Galaxies, galaxy clusters, and the large-scale structure of the universe all show gravitational evidence for enormous amounts of matter that produces no light and interacts with nothing electromagnetically. The Standard Model contains 0 candidates for dark matter. Every particle it describes has been studied intensively, and none of them accounts for the missing mass. Dark energy is absent. About 68% of the total energy content of the universe consists of dark energy, the force driving the accelerating expansion of the universe. The Standard Model does not explain it. The matter-antimatter imbalance is unexplained. The Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other completely, leaving nothing. The universe exists because slightly more matter than antimatter was produced. The Standard Model can describe this imbalance mathematically, but can't explain why it happened. These are enormous open wounds. The Standard Model is the most precisely tested scientific theory ever produced, and it accounts for roughly 5% of the universe's actual content. The other 95% falls outside its description entirely. Extra dimensions don't solve all of these problems, but they address several of them at once. A working theory of quantum gravity emerges naturally from string theory's extra-dimensional framework. Dark matter candidates appear in the form of hidden sector particles or brain matter. The hierarchy problem, gravity's weakness, finds a clean solution. Every open wound in the standard model is a direction. And many of those directions point toward physics beyond our 3 dimensions of space. The question is whether the signal that starts answering them will come from where scientists currently expect. 27% of the universe is invisible. Every galaxy you've ever seen in an image, every star cluster, every nebula, every spiral arm glowing with light, all of it represents a fraction of the actual matter content of the universe. The rest is dark matter, present everywhere, measurable by its gravity, invisible to every other kind of detection. The evidence for dark matter is overwhelming. In the 1970s, astronomer Vera Rubin measured the rotation speeds of galaxies. A spiral galaxy should rotate with stars in its outer regions, moving slower than stars near its center, just as outer planets in our solar system orbit more slowly than inner ones. The outer stars and galaxies Rubin measured were moving far too fast. Something was adding gravitational force from outside the visible structure of the galaxy, keeping those outer stars from flying off into space. Invisible mass surrounding the galaxy, a dark matter halo, fit the data perfectly. Since Rubin's work, dark matter has been confirmed through gravitational lensing, where the light from distant galaxies bends around invisible concentrations of mass. It's been confirmed through the behavior of galaxy clusters colliding with each other, where the visible matter and the gravitating mass separate in ways that only make sense if most of the mass is in a form that doesn't interact with light. It's been confirmed through the large-scale structure of the universe, where the web of galaxy filaments forms along the skeleton of dark matter distributions present since shortly after the Big Bang. Dark matter exists. The open question is what it is. The extra dimension framework offers a candidate that doesn't appear anywhere in the standard model. If our universe is a brain inside a higher dimensional bulk, there's nothing preventing other brains from existing in that bulk. A parallel brain could contain matter, ordinary matter with its own protons, electrons, and forces, all locked electromagnetically to its own surface. That matter would be completely dark to us. It can't emit light that crosses into our universe. It can't absorb our light. It can't be touched by our electromagnetic fields. But its gravity crosses the gap in the extra dimension freely. We'd feel the gravitational pull of an entire parallel world of matter without seeing a single photon from it. To us, it would look exactly like dark matter, an invisible source of gravity shaping the structure of our galaxy. The observational signature of this scenario is subtly different from other dark matter candidates. If dark matter is brain matter, it would cluster and distribute in space differently than if dark matter were exotic particles floating through our universe. The exact shape of dark matter halos around galaxies and clusters carries statistical information about the nature of the dark matter. Current surveys mapping dark matter distributions across the universe are precise enough to start distinguishing between these scenarios in principle, though the data sets aren't yet large enough to make a definitive call. If future dark matter mapping finds distributions consistent with brain matter rather than exotic particles, it would simultaneously solve the dark matter problem and provide evidence for extra dimensions. 1 measurement. 2 massive mysteries resolved. But what happens if 2 brains don't just sit parallel to each other, but actually collide? The Large Hadron Collider as currently built is already the most powerful particle accelerator in history. But particle physics has a principle that has driven machine design since the field began. When the current machine reaches the edge of the physics it can probe, you build a more powerful one. The immediate upgrade is the high luminosity phase of the current collider. Luminosity in accelerator physics refers to the rate at which collisions happen per unit of beam cross-section. Higher luminosity means more collisions per second at the same beam crossing point. The goal of the upgrade is to increase the number of proton-proton collisions by roughly a factor of 5 to 10 compared to the current run. This doesn't increase the energy per collision. The collision energy stays at 13.6 tera electron volts. What changes is the statistical power. More collisions mean more data. More data means smaller statistical uncertainties. Signals that currently sit at the edge of detection, producing results that could be noise or could be real, would either emerge clearly or disappear definitively with 10 times the data. The upgrade requires replacing or refurbishing large sections of both major detectors, new silicon pixel trackers with finer granularity, upgraded calorimeters able to handle the higher collision rate without losing track of individual events, more powerful computing infrastructure to process the faster data stream. Every persistent anomaly in the current dataset gets re-examined with dramatically improved statistics after the upgrade. The soft excess in high-mass lepton production, the deviations in particle decay rates, the missing energy events that sit slightly above standard model predictions, all of these get tested with far more data points. For the extra dimension searches specifically, the upgrade matters in a second way. Higher luminosity at the same energy means better sensitivity to rare processes. A Kaluza-Klein particle produced at a rate of 1 event per trillion collisions would appear multiple times in the upgraded dataset, enough to form a visible statistical bump. That same particle would have been completely buried in the current data. Beyond the luminosity upgrade, the physics community is already planning the next machine. The Future Circular Collider, proposed to run in a new tunnel 100 kilometers in circumference, would operate at roughly 6 times the current collision energy. Some theoretical models predict that Kaluza-Klein particles or microscopic black holes would become accessible only at energies available in that new machine. That proposal is in the planning and approval stages. It would not operate until the second half of this century. Between the high luminosity upgrade and the future machine, physicists expect to push the extra dimension search across the full range where current theories predict signals should appear. If nothing is found across that full range, the theoretical landscape for extra dimensions contracts severely. The hierarchy problem would remain unsolved, and physics would need to find a different answer. But if a signal appears in the upcoming luminosity data, it would arrive before most people alive today reach middle age. A single confirmed event, a Hawking burst, a Kaluza-Klein resonance, a graviton escape, would change physics overnight. Stephen Hawking's calculation about black hole evaporation solved one problem and created another one that turned out to be even harder. Hawking showed in 1974 that black holes radiate particles and slowly lose mass. Over an enormous span of time, a black hole completely evaporates. For a stellar black hole, this takes longer than the current age of the universe many times over. But eventually, the math says, it's gone. Here's where the problem starts. Everything that ever fell into the black hole went in carrying information. The arrangement of atoms in a book, the quantum state of each particle, the structure of every object that crossed the event horizon. All of that information went in. When the black hole evaporates through Hawking radiation, the radiation it produces is thermal. It's essentially random, carrying no specific information about what fell in. The book is gone. The quantum states are gone. Physics calls this information loss, and it's catastrophic for the rules of quantum mechanics. Quantum mechanics requires that information can always be recovered in principle. It can be scrambled, hidden, redistributed, but never destroyed. Hawking radiation appears to destroy it. This conflict became one of the deepest unsolved problems in theoretical physics. Hawking himself initially argued that information was genuinely lost. Most quantum physicists disagreed. The debate ran for decades. Now scale this down to a microscopic black hole produced in a particle collider. The same problem applies in miniature. Two protons carry specific quantum states when they collide. If the collision produces a microscopic black hole that evaporates through Hawking radiation, does the quantum information from those original protons survive in the outgoing particles? If extra dimensions exist, and the microscopic black hole is a genuine quantum black hole rather than a classical one, the evaporation process might carry more information than Hawking's original calculation suggested. The extra-dimensional structure of the black hole changes how its event horizon behaves at the quantum level. Some theoretical models predict that Hawking radiation from these quantum black holes would actually carry encoded information about the original quantum states, solving the information paradox in the collider setting. Detecting this would require measuring the quantum correlations between the particles emitted during a Hawking evaporation burst. The correlations would be subtle. Individual particles in the burst look thermal and random. But across many such bursts, statistical patterns in the correlations would reveal whether information is being preserved. This makes microscopic black holes at the collider a laboratory for one of the hardest problems in quantum gravity. The problem of where information goes when it falls into a black hole, a problem that applies to black holes across the universe, might be testable right here in a machine buried under Switzerland. The collider becomes a quantum gravity laboratory, a place where the rules governing the deepest structure of reality can be tested in conditions that don't exist anywhere else on Earth. And every confirmation, every anomaly resolved, every parameter constrained, changes what the next generation of physicists inherits. Because confirming extra dimensions wouldn't just close a chapter in the physics textbooks. Every physics course taught at every school on Earth starts with a specific picture of space, 3 dimensions, length, width, and height. You can go north or south, east or west, up or down. Every direction you can physically move in fits into these 3 axes. Space is 3-dimensional. This is not presented as a theory or a model, it's presented as the basic description of where you are. That picture would be wrong. A confirmed extra dimension would require rebuilding physics education from the ground up. The way space itself is taught, described, and visualized would have to change. But the effect goes much deeper than curriculum revision. General relativity describes gravity as the curvature of a 4-dimensional spacetime. With extra dimensions confirmed, that 4-dimensional spacetime becomes embedded in a higher dimensional structure. Every calculation ever made about the bending of space around a massive object, the behavior of black holes, the expansion of the universe, would need to be revised to account for the extra dimensional geometry underneath. The fundamental constants of physics, the numbers that define the strength of gravity, the mass of the electron, the speed of light as measured in our universe, might all be derivable from the geometry of the hidden dimensions. String theory predicts this. Different shapes of the compactified dimensions produce different values for these constants. Confirming extra dimensions would turn these numbers from arbitrary facts of nature into consequences of a geometric structure. That's a profound shift. Right now, physicists treat the constants of nature as input values. They're measured from experiment and plugged into equations. Understanding why they have the values they do is an open question. If the values flow from dimensional geometry, then the question of why the universe has the physical laws it does becomes, in principle, answerable. The question of why anything exists at all gets reshaped too. If the Big Bang was triggered by a brain collision, a topic that comes next, then the universe's origin is a physical process within a larger structure. not a singular event at the edge of time. The beginning of our universe becomes one instance in a larger cycle of events, governed by the physics of the bulk. This change propagates outward from physics into every field that physics touches. Chemistry is applied physics. Biology is applied chemistry. Every model of how stars form, how planets develop, how life emerges, would be situated inside a richer and stranger context. The philosophical consequences don't stop at science. Every major tradition of thought about the nature of reality, whether scientific, philosophical, or religious, has assumed a universe of 3 spatial dimensions. A confirmed 4th or 5th or 6th spatial dimension doesn't invalidate those traditions, but it forces them to expand their framework significantly. What space is, what time is, what it means to exist in a universe that is itself just one surface within a larger geometry. These become pressing questions with actual physical content. A discovery at a particle collider 300 feet underground would change the meaning of the word reality. And the scenario that might have created our reality in the first place is one of the most violent and strange ideas physics has ever produced. Our universe might have a neighbor. Under the brain world framework, nothing prevents multiple brains from coexisting inside the bulk. Our brain could be one of many surfaces floating in the higher dimensional space. These parallel brains could contain matter, forces, and possibly even structures as complex as galaxies. They could be complete universes in themselves. We would know nothing about their contents. Their light stays on their surface, their electromagnetic forces stay on their surface. Every particle they contain is locked to their brain, exactly as our particles are locked to ours. No signal, no message, no observation could cross the gap between brains through electromagnetic channels. The only crossing is gravity. From our perspective, a nearby brain with matter on it would look like a distributed gravitational source with no visible origin. We'd measure gravitational attraction toward a region of space that our telescopes show as empty. No stars, no gas clouds, no dust, nothing that emits or absorbs light. Just gravity, pulling on us from somewhere we can't see. Some versions of this idea propose that dark matter is specifically this: matter distributed across a parallel brain, separated from ours by an extra-dimensional gap so small it's measured in fractions of a proton diameter. The parallel brain's matter doesn't move through our universe, it doesn't interact with our particles, it just gravitates. The separation between brains could be dynamic rather than fixed. In some models, brains can move through the bulk. They drift, driven by forces operating in the extra-dimensional space. The gap between our brain and a neighboring one could shrink over time. A neighboring brain could currently be moving toward ours. If that's happening, the gravitational effect on our brain would change over time. The pull from an approaching brain would increase. The distribution of dark matter in our universe would shift in subtle but measurable ways as the parallel brain's position changes. Surveys mapping dark matter distribution across cosmic history already look for exactly this kind of time-varying signal. Finding it would require extraordinary precision, but the datasets being assembled by current and planned telescopes are approaching that level. The gap between brains might be shrinking. The neighbor might be closer now than it was 1 billion years ago. And if that gap ever closes to zero, the collision that follows would be an event of almost incomprehensible violence. An event that, according to one theoretical model, humanity has already lived through. 2 universes approaching each other through the bulk, separated by a gap in the extra-dimensional space. Moving closer, drawn together by gravitational forces, operating in dimensions we can't see. And then, at some point, the gap closes. The surfaces touch. The collision of two brains releases energy on a scale that dwarfs any other event in cosmology. Every point on both brains collides simultaneously. The energy from both surfaces, accumulated across the entire spatial extent of both universes, converts into heat and radiation at the moment of contact. The temperature rises to conditions beyond any scale our current physics can properly describe. Sound familiar? Paul Steinhardt and Neil Chirok proposed in the early 2000s that the Big Bang was exactly this: a brain collision. Our universe exists on a brain. Another universe exists on a parallel brain in the bulk. The two brains drifted toward each other over an enormous span of time, passed through a period of extreme low energy, and then collided. The collision is the Big Bang. Under this model, called the ekpyrotic scenario, the Big Bang is not the beginning of everything. It's the most recent in a series of collisions between our brain and the neighboring one. The brains collide, rebound, drift apart, slow down, reverse direction under the pull of interbrain gravity, approach again, and collide again. The universe runs through this cycle repeatedly. Each collision resets the contents of our brain, producing conditions that look like a Big Bang from the inside. Time doesn't begin at the Big Bang in this model. It extends before it, through the previous cycle. The universe has no singular origin. It has a history stretching back through multiple cycles, each one beginning with a brain collision and ending as the brains drift to their maximum separation. The ekpyrotic scenario makes predictions about the cosmic microwave background radiation, the afterglow of the Big Bang that still fills the entire sky. It predicts a specific pattern of temperature fluctuations in that radiation that differs slightly from the predictions of standard inflation theory. Current measurements of the cosmic microwave background are not yet precise enough to definitively distinguish between the two. The next generation of space-based telescopes, designed to measure the polarization of the cosmic microwave background with far greater sensitivity, should be able to tell the difference. If they find the ekpyrotic pattern, the Big Bang becomes a collision. Our universe's origin becomes a physical event in a larger history. And the question of what happened before the Big Bang gets a concrete answer. The cycle didn't start with us, and it won't end with us either. But even with all of this theoretical richness, the deepest question isn't about brains colliding or dimensions curling. It's about whether any of this is reachable at all. The Large Hadron Collider accelerates particles to energies around 13.6 tera electron volts. The proposed future circular collider would reach around 100 tera electron volts. These are genuine leaps. Each upgrade opens new windows in physics. But the Planck scale sits at an energy roughly 10 million billion times higher than the future circular collider's target. If string theory is correct and extra dimensions are compactified at the Planck length, reaching them directly would require an accelerator that converts a significant fraction of the sun's total energy output into particle collisions. An accelerator that would need to be built on the scale of a solar system. That's not engineering. It's a different category of problem entirely. Physicists are honest about this. Direct access to the Planck scale is, with the current understanding of physics, physically impossible for a civilization operating on a single planet or even a single solar system. The energy requirements exceed anything achievable by any civilization running on matter and energy alone. So the question becomes whether indirect probes are enough. Can humanity learn everything about extra dimensions without ever directly reaching the scale where they live? The evidence from other areas of physics is encouraging. Scientists have never directly touched a quark. They've never held a neutrino. They've never observed a single Higgs boson with a naked eye or a simple microscope. Every particle discovered in the last century was found indirectly, through the statistical patterns of other particles it produces or the energy it carries. The Planck scale is extreme, but indirect signatures of Planck scale physics can propagate down to energy scales the collider can reach. Kaluza-Klein recurrences, graviton escape events, Hawking bursts, these are all indirect signatures. They appear at energies far below the Planck scale while pointing to physics operating at it. The real limit isn't the Planck scale itself. The real limit is whether the indirect signatures are strong enough to distinguish from background noise at achievable energies. Some theoretical models predict signatures that would be clear even at the collider's current energy. Others predict signatures only accessible at the future circular collider's energy. A small number predicts signatures only accessible at Planck-adjacent energies. If the collider and its successor find nothing, it won't mean extra dimensions are impossible. It will mean that the models predicting accessible signatures are eliminated. Physics would need to develop new frameworks where extra dimensions, if they exist, produce effects at even higher energies than planned machines can reach. That would be a hard result. Science has survived hard results before. The history of physics is full of beautiful theories that turned out to be wrong and led to better ones. If extra dimensions are real but forever unreachable, that too would be a discovery. The discovery that the universe is structured in a way that places its fundamental geometry permanently beyond human access. But scientists are not ready to accept that limit yet, because the window the current data leaves open is real, and the next dataset could close it with a confirmed signal. Physics doesn't collapse if extra dimensions go undetected, but it faces a serious reckoning. The hierarchy problem remains. Gravity stays inexplicably weaker than every other force, and there's no clean explanation available. The standard model sits with its open wounds, no quantum description of gravity, no dark matter candidate within its particle catalogue, no account of dark energy, no explanation for the matter-antimatter imbalance. String theory takes the hardest hit. The entire mathematical architecture of string theory requires extra dimensions to function. If every experiment capable of probing extra dimensions at accessible energy scales finds nothing, the theory either needs to retreat entirely to the Planck scale, making it permanently untestable in practice, or it needs to be modified in ways that haven't been worked out yet. A theory that makes no testable predictions isn't scientific. This is the critique string theory has faced for decades from physicists who prefer approaches grounded in currently measurable phenomena. If the collider, its successor, and every future machine within foreseeable engineering reach finds no sign of extra dimensions, that critique gains significant force. Other solutions to the hierarchy problem exist. Supersymmetry proposed that every known particle has a heavier partner, a symmetry between matter and force particles that would naturally stabilize the mass of the Higgs boson without requiring extra dimensions. The collider searched for supersymmetric particles extensively and found nothing. The most straightforward versions of supersymmetry are ruled out. The remaining versions require the supersymmetric particles to be heavier than current machines can reach. Technicolor models propose that the Higgs boson is a composite particle rather than a fundamental one, which would also resolve the hierarchy problem differently. These models have their own experimental constraints and their own open questions. Each alternative carries its own cost. Extra dimensions would have been the cleanest, most comprehensive solution. Losing that option means accepting a messier theoretical landscape. But the absence of extra dimensions, if confirmed, would also clarify the path forward. It would eliminate a large class of theoretical options and force concentration on what remains. Science narrows by ruling out. Every closed door is a map of where the answer doesn't live. The community wouldn't stop, it would recalibrate. New theoretical ideas would emerge, as they always do, from the friction between expected and observed. And the question that launched this entire search, why does a refrigerator magnet beat the gravity of an entire planet, would still be waiting for an answer. The universe doesn't owe us a solution we can reach. But it does leave evidence everywhere, and every experiment designed to find that evidence changes the conversation, whether the result is a discovery or a boundary pushed further into the unknown. The next result is coming. And if it happens to be a discovery, the world changes in a single afternoon. Imagine a physicist sitting at a screen somewhere in the global computing network. It's a normal working day. Data from the previous collider run is being processed through the analysis pipeline. The algorithms are doing what they always do, sorting events, scoring them, flagging anomalies. An alert fires. A cluster of events in the high energy range shows a pattern the algorithms haven't seen before. Multiple particles radiating outward from a single collision point in a thermal distribution that doesn't match any known standard model process. The outlier score is enormous. The probability that this is a statistical fluctuation is vanishingly small. The physicist checks the data, then checks it again, pulls up the event display and looks at the actual particle tracks, calls a colleague, sends a message to the analysis group. Within hours, the entire collaboration is looking at the same data. This has happened before at the collider, always resolving into a known process after deeper analysis. But this time, as more experts run through the checks, the signal holds. CMS sees it. Atlas, analyzing its own independent data set from the same collision period, sees it too. The event characteristics match the predicted Hawking evaporation signature for a microscopic black hole, with properties consistent with a universe containing extra dimensions. The particle multiplicities, the energy distribution, the thermal curve, all of it lines up with what theorists wrote down decades ago and coded into the detection algorithms. Scientists spend weeks re-examining every possible systematic error. Every alternative explanation gets tested and ruled out. The statistical significance climbs past the threshold. Past it by a wide margin. The announcement goes out. In the hours after, every physics department in the world stops its normal work. The news crosses into general coverage. The confirmation of extra dimensions beyond our three-dimensional space, the proof that our universe is embedded in a higher dimensional structure, becomes the story everywhere simultaneously. What follows is a change in human understanding of reality that has no precedent in modern science. The discovery of the electron changed technology. The discovery of the atomic nucleus changed warfare and energy. The discovery of the Higgs boson completed a theory. This discovery changes the question of what space is. Every field that touches physics begins asking new questions. Cosmologists recalculate the universe's history in a higher dimensional framework. Dark matter searches pivot toward brain matter as the primary candidate. String theory gains its strongest observational support in history. The philosophical conversation about the nature of reality expands to include physical dimensions that human beings have never perceived and can never directly experience. A refrigerator magnet beat the gravity of an entire planet. That observation, sitting quietly in the middle of the hierarchy problem for decades, pointed here. To a machine buried under Europe. To data processed across a global network. To a single event that shows our universe is smaller than we thought, embedded in a structure larger and stranger than anything written in a textbook. The real scale of things was always there. It just required the right question to start seeing it.